Alright guys, we continue on with the section 2.2 notes, which is all about graphing functions. Okay, so we begin with the definition, a very formal math definition for the graph of a function. When we graph a function, what we're looking to do is graph the set of all points. And we can think of those points in function notation, x, f of x, input, output. Or we can think of it as x comma y. We will be graphing these on xy planes, x horizontal, y vertical, that makes the function true. Math students that feel comfortable in math, when they look at a graph, they're not necessarily seeing the shape of the graph, although they are. That is one of the properties of a lot of graphs that we'll talk about, is its unique shape to it. But knowing that that shape, whether it be a line or a curve, is made up of an infinite amount of points that, if it were plugged into the function, would make the left side equal the right side. So for example, the point 3, 4 is on the graph of f of x equals 2x minus 2, because if we plug in the x, the 3, for that x, and the output, or the f of x 4, right there, well, let's check out what happens. 4 equals 2 times 3 minus 2. Does 4 equal 4? Yes, it does. And we would certainly know that the point 3, 4 is on that graph. A really great ACT, SAT question. Them asking you if a point is on the graph of a certain function. And it could be, they love on the ACT, SAT giving you a function that you don't necessarily know how to graph or know what it looks like. But if you can very simply plug in the x, the input and the output into your function, should be an easy question. So be aware of that on the ACT, SAT. Parent functions. A parent function is the basic shape and properties of a given classification of function. Now, based on our brainstorming the other day, a lot of the things we're going to write down in this set of notes is going to be what we talked about the other day. Okay, so the first one we'll talk about is a linear function. The linear function would have a singular variable raised to the first power, okay, or it could be f of x equals a number. That would be a linear function as well. It creates a line going on forever in both directions, and that would be a graphical representation of that. Okay. We could have a quadratic function. The parent quadratic function would be f of x equals x squared. It has a name for its shape as well. The shape of a quadratic function would be a parabola. Okay. Also, if we raise this to the 4th, the 6th, the 8th, the 10th power, all of the even powers would fit a lot of the same properties and certainly the same shape of a parabola. Okay, we start adding different terms to your quadratic function. That's when some things start to change. A cubic function. The parent cubic function would be x to the 3rd. No fancy name for the shape of a cubic function, but the graph would look like this. And all odd-powered parent functions would look similar to this. Okay, how would they actually change as we go up in powers? They would actually increase and decrease faster, which would make the graph narrow. With the even powers and the odd powers, the graph would start to narrow. We also have the square root function. The square root of x. The square root function looks like that. Okay, we'll talk about a little bit more numerically about why this is the case, but you guys can probably imagine as you're thinking about, or if you are thinking about, why is a square root function, why does the graph of a square root function look the way it does? Think about it numerically. Think of inputs and outputs you might get out. Maybe even what inputs could we not put into the square root function, which would determine that it actually doesn't go to the left of the y-axis into our negative inputs or negative x values. We can have a cube root function, the cube root of x. The cube root function would look something like that. Again, you can think numerically if you want the reasoning behind why the cube root function looks like that. We will also study rational functions. We'll get more into that during second semester. But we do talk about its parent function, 1 over x. A rational function is really defined as a function with a variable in the denominator of a fraction. The parent rational function actually has an asymptote at the y-axis. And as we talked about domain and range in section 2.1, I'm sure you can figure out why it has an asymptote there, especially with that variable there in the denominator. And the last one we'll talk about on these notes would be an absolute value function. F of x equals the absolute value of x. Those absolute value bars mean absolute value. And just like you guys learned a long time ago, the parent function of the absolute value function is in the shape of a V. Okay. So we will talk a lot about many of these different functions throughout the course of the first semester, the first year, all of pre-calculus advanced. So familiarizing yourself with the properties of the parent functions of the linear, the quadratic, the cubic, the square root, cube root, rational functions, and absolute value functions can help you when you're asked to graph. Instead of having to rethink about what the different shape of every single function that you want to think about or want to graph is, you can start to make the connections about what all cubic functions look like, and then adjust that to different specific cubic functions. And the last thing we'll talk about today is the definition of a continuous function. Okay? A very big calculus topic that we start talking about in pre-calculus is the concept of continuity. Okay, so a continuous function, the word continuous, okay, kind of plays in here. There's a very formal math definition that actually uses limits, and since we haven't learned limits, we really don't want to put that into a formal definition, but basically a single, unbroken curve graph would be said to be a continuous graph or function. Okay. All right, so one of the tests that we talk about with students to make it very simple in terms of trying to figure out whether something's continuous if we have a graph to look at is, can you graph the entire graph or trace the entire graph without lifting up your pen or pencil? Okay, so if we had a graph that looked like this, maybe we'll even put our rational graph back on here, the parent function. Okay, this would be discontinuous or not continuous. Okay, I cannot graph this all without picking up my pencil. The asymptote here at the y-axis causes me to jump from here to here. Okay, this is not continuous. Another example of a problem with continuity would be what we call a hole. There's a hole here. I graph and then I have to pick up my pencil, jump over that hole, and continue on with my line. This is discontinuous. One of the main graphs that you might see that is not continuous or discontinuous would be a piecewise function. Of course, if a graph is in different pieces, there is a possibility that it might be discontinuous, or not continuous. Let's give you one that is continuous. All polynomial functions are continuous. Quadratics, cubics, raised to the fourth power. Okay, anything from graphing back in in Algebra 2 trig, you guys know this would be the graph of a polynomial function. This graph is continuous for obvious reasons. One unbroken curve or graph, this function, this graph, is continuous. We'll do more examples with continuity. We'll do more examples and lots of graphs when we get to our examples in class.